Okay, there's another technique that we can use to put this in the vertex form instead of the standard form. Okay, and so if I have y equals 2x squared minus 8x plus 11, and I want to put that in vertex form, we can use the algebraic process that we call completing the square to do that as well. Okay, so I'm going to show you what that looks like next. The steps are going to be as follows. I'm going to get the constant term, the c term, I'm going to put that onto the other side with y. So I'm going to write it as y minus 11, 2x squared minus 8x. Okay. And then from there, what I'm going to do is I'm going to manipulate the x's here. But the first thing I'm going to do, though, is that if there's a number in front of x, I'm going to factor it out. Okay? And then the way I'm going to set my problem up is I'm going to write x squared minus 4x plus blank. And I'm going to leave that blank for the time being. Okay? All right. So this process only works if the leading coefficient on the x squared here is 1. Okay? So this process that I'm about to do here, that I'm about to show you, okay, only works if this is a 1. So if there's a 2 there, it has to be factored out. Okay, even if this leaves a fraction for our b value here, that's okay. Okay, we still have to factor it out. All right, now the other thing that we need to make sure I do here on the left side is that if I'm going to add something, I added a blank. I don't know what it's going to be yet. We're going to find out in a minute. Okay, but if I add something to the right side of the equation, what am I going to have to do to the left? Remember, an equation is a balance. So if I add something to the right, I got to add it to the left also. Okay, so then what we're going to add here is a strategic number. Okay, what's going to go in that spot right there, okay, is always going to be half of the middle term, half of b squared. Okay, so what's going to go in there is b over 2 squared. So in general, whatever that b value is, we're going to divide it by 2, and then we're going to square it. So in our particular case, we're going to take 4, okay, negative 4 specifically, and divide it by 2. That gives us negative 2. But if we square that, we're going to get positive 4. And you'll notice when I did this originally, I put a plus here. Because no matter what, when I square something, it's always going to be what? It's always going to be positive. Now, once we do that step, okay, we also need to do that over here. But here's where we have to be careful, because on the right side, we put a 4 in the blank. But did we really add 4 to the right side? What did we really add? Yeah, we really added 2 times 4, didn't we? So that means we need to put an 8 here. Okay, so we added 8 to the right, so we're going to have to add 8 to the left. Okay, simplifying the left-hand side, I'd get y minus 3. Now here's the deal with why we added that strategic number. Okay, if we add that strategic number, okay, then this is always going to factor into a binomial squared. Fair enough? It's always going to be x. It's always going to have the same sign as what the b term has. Okay? And then the number that's going to go here is always going to be b over 2. And what was b over 2? Okay. It was 4. 4 divided by 2 is 2. And so that number right there is going to be a 2. So the number that goes here is always b over 2 squared. The number that's going to go here is always just b over 2. Questions? Ash? Question? Okay. All right. Now, once you have it factored, okay, then the final step is just to write it in the right form, which means take that, square that is, 3, and add it to their side. And you notice that how does this compare with the answer we got last time? Isn't that the same thing we got last time when we did it the other way? True? Okay. So we've had some experience with completing the square. I went through that very slowly, but is that any different than when we learned how to do that with solving equations by completing the square? It's the same thing. We had that b minus 2. That should all look familiar. We did that in chapter 1. So b over 2 all squared, okay, and then that factors again to b over 2. So hopefully that's a technique that we remember. We'll continue to practice that. I want to do one more of those just to illustrate. This time we'll do y equals, let's say, I'm just going to do x squared minus 6x plus 9, let's say. Okay. And if I want to put that into vertex form, let's go through the steps again. We're going to move the 9. Okay. This time we skip a step because there's no factoring. We got the x squared already with a 1 coefficient, which is good. So now we can just go right to y minus 9 plus blank, and x squared minus 6x plus blank. And in this particular case, our blank is going to be b over 2 would be 3. 3 squared would be 9. And this time we really did add just a 9 to this side because there's no multiplier here. So we're going to have 9, 9. And then if we subtract those two, we're going to get y because those two are opposites obviously on the left. And then when we factor this, we're going to have x minus, and b over 2 would be 3. So we factor that to y equals x minus 3 all squared. Now, one thing that we want to ask here then is what's our vertex then? If I put it in vertex form, okay, the h value is, or the general form is x minus h. So the x coordinate is 3. What about the y coordinate here? 0. And one thing also is if you have a calculator, is this something that we could check by graphing? Could we graph either version and make sure that the vertex is actually at 3, 0? Okay. Questions so far? Alright. Alright, I want to look at, there's a couple more examples I want to look at, just more stuff regarding parabolas and quadratic equations. Okay. On this one, I'm not going to actually do the completing the square on this, but ultimately if we wanted to, it says use completing the square to describe this graph. Okay, we could do the same thing we just did in the last problem to do that. If we were to graph it, we would wind up with this picture. Just a couple of key features here. We could find the vertex here. It looks like the vertex is at 3 halves and 1, like they said. Okay, we can find the x-intercepts also. One thing that I want to make sure we're clear on too, and I've discussed this already earlier, but I want to point it out one more time. Okay, if we want to find the y-intercept of any graph, okay, whether it's a parabola or a line or otherwise, okay, if we want to find the y-intercept, okay, if we're on the y-axis, that means the x-coordinate is 0. So the general strategy, once again, is to plug in 0 for x and solve for y. In this particular case, we'd get 0, negative 8. If we wanted to find the x-intercepts, okay, whether it's a parabola or a line or any of other functions, we're going to plug in 0 for y and solve for x. Now, what's that going to mean for us in this particular case? Okay, is that going to be something that we can just solve by looking at it? No. Okay, in this case, it's a quadratic equation, so we're going to need to, I would factor out a negative 4 here, and then maybe it's factorable. Okay, if it's factorable, then we can find the two solutions. What if it's not factorable? Then we have to use the quadratic formula. Okay. All right. Okay, the one last problem I want to finish up with here. Actually, I lied. I want to show you this one slide real quick. This is that the little box that's in your book talking about the characterizations of a quadratic. We had one of these yesterday with a linear. Okay. Verbally, we call a quadratic equation, it's a polynomial with degree 2. Okay. Algebraically, we can write it in either standard form or we could write it in vertex form. Okay. Either way. And then graphically, we know that it's always going to be a parabola. It's always going to have vertex hk. The axis of it, axis of symmetry, is going to be x equals, mistake, so make sure you have that. I don't know if that's wrong in the book too or not, but it'd be annoying if it was. And it's not. The book has it right. The slide's wrong though. Okay, so make sure it's x equals h. It's always the x coordinate of the vertex is where our axis of symmetry is. Okay, we know it opens up if a is greater than 0, down if a is less than 0. Okay, the initial value or the y-intercept is always c, because if we plug in 0 for x, we're always going to get that c value. Okay, and then also the x-intercepts are going to be found by quadratic formula, or what else? What else could we maybe find them with? Could be completing the square or factoring, right? So we could factor or complete the square, one of those two. Best bet usually, and I think I said this before when we learned that the first time about completing the square to find the solutions to the equation. Okay, I would rather use the quadratic formula than completing the square. So if it's your choice, that's what I would do. Okay, one final problem I want to look at here is going to involve an idea from science, okay, which is free fall motion. And the formula that's going to be used for any free fall motion problem is going to be this position, this S, okay, the height of an object if it's in free fall. So, and keep in mind, as soon as if we throw an object or we shoot it out of a gun or we drop it from a cliff or whatever, as soon as that thing leaves our hand or the barrel of the gun, etc., okay, the only force acting on that is gravity. Okay, so therefore it's in free fall, we say. Okay, so as soon as the object is in free fall, then it's governed by these equations. Okay, the height of it at any given time is going to be negative 1/2 gt squared plus v sub 0 is the initial velocity times the time plus s sub 0, which is the initial height. Okay. The velocity of the object is always going to be negative gt plus v sub 0. So a couple things. First of all, the g part. Okay, g is always a constant. G is either negative 32 feet per second squared or it is 9.8 meters per second squared. Those are the acceleration due to gravity constants near the Earth's surface. Okay. So how did they get those numbers? By experimenting. Okay. So ultimately, if we dropped an object right here, okay, its acceleration, okay, as it goes towards the Earth, it's accelerating at a rate of negative 32 feet per second squared. Okay. So these g's are always given. Okay. Which one do you use? It depends on what the units are like in the problem. If your problem has meters in it, then you're going to use this one. If your problem has feet in it, then you're going to use this one. Okay. All right. And again, the key issue is the time is the variable. Okay. V sub 0 is the initial velocity given. S sub 0 is the initial height given. Okay. So let's go ahead and use those. Okay. With a particular problem. Okay. I'm going to say that we drop an object from the cliff. Okay. So say we drop a rock down the cliff, let's say. Okay. And if I write a position function for that, okay, it's going to be negative, and I'm going to say that the cliff is 60 feet tall, let's say. Okay. Fair enough? Okay. So if the cliff is 60 feet tall, then my position equation in general is going to be negative 1/2 gt squared plus v sub 0 t plus s sub 0. Okay. So let's fill in the blanks for this situation. My negative 1/2, what's my g going to be if I'm in feet? 32. It's either 32 or 9.8. Those are your only choices. And so I'm going to have t squared here. And my initial velocity here, if I just drop the rock, okay, then what's my initial velocity going to be? Okay, if I just drop it, am I giving it an initial velocity? No. So the initial velocity would be 0. If I threw the rock, then I would have some initial velocity. True? But I'm going to say in this case that I'm just going to drop it. So therefore I'd have 0 times t. And then my s sub 0 here is going to be 60. That's my initial height. So with that said, then if I simplify that, my equation for the height at any time, oops, I'm going to get negative 16t squared plus 60. Okay, that equation right there is going to give me the height of the rock at any time. Okay, Sam, question?
Where did you get the 32?
Okay. Remember, when we're near the Earth's surface, you have two numbers that you need to know. 32 is for feet per second, and 9.8 is for meters per second. These are given numbers. These never change. The only reason these would change is if we flew to another planet. Because on the moon, they'd be different, because things don't accelerate fast on the moon. The gravity's not as big. True? Okay, so these numbers are just numbers that we use for Earth. If it was a different planet, then we'd have different numbers. Okay. So with that said, we have information about what's going on with this object. Okay, at any time, we could figure out what its height. So if I wanted to figure out where this object was after 1 second, I could put 1 in here, and I could figure out that it's negative, or that it's 16 plus 60. That'd be 46. So it'd be at 46 in the air. 2 seconds, I could figure it out. Could I figure out when it hits the ground? What would I do to figure out? What would I do with that equation to figure out when it hits the ground? Jared? Sure. Wouldn't I just set the height equal to 0 and then solve that quadratic equation? Wouldn't that give me when? Okay. So we can answer some questions here. We also were given that this the velocity formula is negative gt plus v sub 0. So if I want to know the velocity of the rocket at any point in time, I would have negative 32t, and that would be it, because what was my v sub 0? It was 0. So if I want to know the velocity at any point in time, I could put that in there. So if I want to know its velocity when I was at 1 second, it would be negative 32. feet per second. Okay. What if I want to know the velocity just the instant before it hits the ground? What would I need to put in here for t? Okay. You know, what question did I just pose up here? This is going to be when it hits the ground, wouldn't it, right? So couldn't I take that time that I find when I do this problem and then plug it into this and find the velocity at that time? And that would be the velocity just before it hits the ground, right? How about the velocity after it hits the ground? It's going to be 0, right? Okay. But like I said, if you find the time when it hits the ground by solving this, you could take that time then and put it into the velocity equation and you could get the velocity just before it hits the ground. True? Okay. Alright, so like I said, most of our work today is going to be dealing with parabolas. Okay. We're going to be talking about some of the features of parabolas, finding vertexes, etc. And then also working with some problems that are real problems involving parabolas as well. Okay.